day in recitation. So let's start. Let's start with some content. All right, so this class is computer systems engineering, right? So the first question I have for you all, what is a system, right? Like, what is a computer system? If some of you want to put in the chat, tell me some examples of computer systems or things that you think are computer systems. There's no wrong answer. It's the first question I'm ever going to ask you. Okay, I would say, yeah, computers, that's a fair computer system. Home network, the 6033 website and servers, for sure. McDonald's cash registers, yeah, those are hooked up to a computer. All sorts of things, all right? The internet, Linux is a system. Facebook is a system, right? Whatever set of databases the registrar uses to perform your audits is a system, right? There's all sorts of things. So the book gives you this definition, right? A set of interconnected components that has an expected behavior observed at the interface with its environment. But you have interacted with these things before. So what we're going to do in this class, the digestive system, a system, not so much a computer system, we're going to teach you how to design and build, so to engineer these systems. And since we're going to spend the entire semester on it, right, there must be something that makes this difficult, right? The thing that makes building systems difficult is complexity, right? Complexity is sort of a vague term on its own. You can think about it as difficult to understand, but that's subjective, right? What is difficult for me to understand might not be difficult for you to understand. Rather than trying to define it precisely, we're going to look for a number of signs that might indicate complexity. So complexity within computer systems might mean there's a lot of components or a lot of connections, some sort of irregular design, or a design that's difficult to describe, a design that requires many people to maintain it, all right? All of these sorts of things. And complexity in systems tends to come from it can come from any number of things, but doing things like adding a bunch of new requirements to a system, trying to maintain really, really, really high utilization of a resource. So like trying to kind of max out the performance of a system, trying to be excessively general, right? Trying to build a system that can do everything instead of like doing one thing well, right? But so how much complexity are we really talking about here, right? Like how big are these systems? So one way to get a rough measure of complexity in computer systems is to think about, well, just how many lines of code does it take to build a system? This isn't the best metric to use. It's going to work for us today. It's fine for a rough estimate. It's also something that you all are familiar with, right? You have written lines of code. So I'm going to give you all a poll. Let's see. Cool. The poll is anonymous. I don't know who, so I won't see what your answers are. And I just want to know, just to guess, I've given you a bunch of different systems. What do you think is the biggest, right? The most line of codes, right? Whichever one you think is the biggest, just about how many lines do you think it is? Okay. There's no reason you would know this coming in. Okay. So just feel free to guess. I'll give it about 10, 15 more seconds or so.
For Facebook, is that only for the facebook.com service, or like all the code Facebook as a company has?
It's all the code that Facebook has. Man, watching these votes come in is fascinating. Okay, awesome. So this is good. I know not all of you had a chance to answer. That's okay. It's just a fun thing. So I'm gonna turn this off. And let's see how close you all were. So I gave you these systems actually in order. So you all did pretty well. So I'll share the results. Facebook is indeed the largest of these systems, right? So in fact, large by quite a lot. So I'm gonna show you this website. I like this website. The data is from, it's a little bit old now, so assume that some of these things have grown. Facebook is probably bigger now. But you should be able to see part of this website on the screen here. So I'll scroll down. So you can see we're looking at things that have like 1 million lines of code. All right, Hubble Space Telescope. I'm really big on space, so 2 million lines of code. Right? 5 million, the number of lines of code needed to repair healthcare.gov. That was a good time. So yeah, here we are scrolling through. Windows is like 25. Oh, where is World of Warcraft? That is an important one to focus on. Yes, 5.5 million lines of code. So here's Facebook. Facebook is around, oh, you can't see the whole side, 62 million lines of code, right? We could have kept going. Google, 2 billion, like all of Google, right? It keeps going. Okay, so I'm telling you all this not because, you know, I'm hopeful that you all are going to memorize all of those numbers. We're not even going to look at those numbers again. But I want you to get a sense of how big we are thinking here. These are really, really big systems. Right, but you saw from those examples, all of those systems, they're doing pretty complicated things. So there's kind of a question of like, in a way, like, why do we care? Why do we care about complexity? Why don't we just accept that, well, these systems are solving big, complicated problems, so we're going to need big, complicated systems, right? The reason we care about this is that complexity limits what we can build, right? The more complex a system is, the more expensive it's going to be to maintain, the easier it's going to be to break, all sorts of things, right? So this is our big focus in this class. All right, dealing with complexity, all right? It limits what we can build. So our first question is just, well, how do we get rid of it? How do we mitigate complexity? The way that we mitigate complexity, right, in this class, is we're gonna follow design principles, all right? We're gonna begin with 2, modularity and abstraction. I will show you some examples of modularity and abstraction in just a second. You're going to see these design principles applied over and over and over in the class. You're going to see lots of other design principles in the class. After 6033 is over, you will start to notice these design principles in all other aspects of your life. Eventually, you will see the entire world through the lens of modularity and abstraction in 6033. So this is the life you have committed to now. All right, so I'm going to introduce you to these ideas by sort of taking you through what for some of you might be your first exercise in designing a system. And you're going to notice potentially something else as we go through this exercise, right? It's that there's not usually a single correct design, all right? Typically what we are dealing with in this class is all about trade-offs, all right? So let's begin. A proper modular system is divided into components or modules such that we can consider the implementation and interfaces of these modules separately. Also, I see in the chat the average of 1 error for every 1,000 lines of code. That's going to come up later. So good segue. Not today, but in a couple lectures. All right. Modular systems are easier to reason about. They are easier to manage because they are easier to change and to improve. Right? It's a lot easier to change a module than to change the entire system. We'll also see examples where modularity reduces what we call fate sharing. All right, so if one module crashes, maybe the others don't. All right, so here's where we're going to start. We are in this class focused on building an Amazon competitor. All right, we're starting off small. The Amazon competitor is known as Katrina's Amazing Web Suite. All right, and so we've decided that we need 2 things. All right, we need servers, right, software to host the website, and then we also need software to render the website, right? So some sort of browser. All right, so let me draw you all, oh, wrong option here. Oh boy. Here we go. Okay, so I'm going to draw for you here. The colors look weird because I have the contrast up. So here's how you might think about that. All right, especially if you are coming from, you know, the world of kind of software. You think, okay, I need a browser, so this will show up. I'll move my hand so that you can see all of this. All right, so I've got a browser class. It doesn't matter what language this in. This is very, you know, pseudo-codey, and you know, it's got some main method that does some stuff. We don't care about the details right now. And I've got a server class. You know, potentially it has a function among many other functions that it might have to load, you know, load a URL. All right, and this is kind of the, this is not a bad idea, right? We've nice object-oriented design. All right, we're kind of thinking, here's my browser module, here's my server module. All right, so I'm gonna take this. Let's imagine that despite this particular pseudocode I use, that this is in Java or something. I'm gonna take this and compile it all, and it gets loaded in this file, kaws.java for Katrina's Amazing Web Suite.java, right? So I've compiled it all, and I'm shipping this out to clients, right? To start, again, our overtaking of Amazon. Okay, but it turns out, as mentioned in the chat, you know, one bug every per 1,000 lines or so, I probably have a bug in here somewhere, all right? And let's in fact assume there's a bug somewhere in the browser and just causes it to occasionally crash, right? Not that often, but occasionally crash, right? Now, if I've set things up this way, this is really bad for me, right? This is all bundled into like one program, one file, right? If my browser crashes, my server is going to crash as well, right? And, you know, all sorts of other things can go wrong. I'll give you some examples in a second. At the same time, this does appear to be the start of a modular design, right? But, you know, is it really, right? Errors can propagate between these modules, okay? So the problem with only thinking of modularity in this sense is that there was nothing here that enforced the modularity. Your compiler, your choice of language protects these components from each other somewhat, but only a little bit, right? So for instance, in Java, if a component crashes, throws an uncalled exception, goes into an infinite loop, something like that, this entire program is going to stop working. In a language like C, oh boy, things are even worse, right? A misbehaving function could overwrite memory, it could do all sorts of things, right? So this type of modularity, it's not that it's bad, but it's soft modularity. Nothing is forcing the interactions among modules to adhere to their defined interfaces or to sort of be protected from one another. And soft modularity is not enough for us in O33, right? What we are going to want in this class is enforced modularity. So it's modularity that is enforced by some external mechanism. There are a lot of different ways to do this. We're going to start with one. All right, so our first big question now is just, how do we enforce modularity? All right, one way to do this is known as a client-server model. All right, and the way this starts is by taking those modules that we had before and putting each of them on a separate machine. Okay, so here's how we're going to start. All right, I have my browser, I have my server. I've given a little bit more detail in the boxes here, right? Because we're gonna deal with a little bit of the internals today. All right. It's not because, again, it's not because we're gonna care today so much about the exact code that's here. It's still gonna be very pseudocodey, but we're gonna care about some problems. All right. So let's get into this. You know, right now I have a browser on one machine. That's what the line is for between them. Server on the other machine. And right now this system is useless. Because right now, I haven't illustrated any mechanism by which the browser might communicate with the server. It's literally like I put one laptop over here and one laptop over here and just sort of look at them. All right, so we're going to send some messages. Okay, these messages are going to matter. So in a little bit more detail, we still expect to see things like the browser loading a URL, the server handling the request for that. And as programmers, these interfaces are nice, right? I would like to still be able to call functions like this. But now that we've split these things into separate machines, we need to do a little bit more work, right? Because now when that browser, tries to load our URL, something's got to get to the server, right? And something's got to come back, right? So we'll start to see this in a client-server model. You'll see sort of code patterns that look like this, right? So we'll talk about these as stubs. This just illustrates, the internals of these functions. They deal with, taking whatever request, formatting it so that it can be sent, say, across a wire, across a wireless channel, across whatever communication channel you want, right? They'll wait for the reply to come back and then, reformat as needed. And in fact, you've heard me now use the words like, request and reply or request and response. And that's usually the type of communication pattern we see here. So those are the words that we'll start to use. All right. So you notice we have, in addition to modularity, which we're talking about, we also have some nice abstractions here. All right. These stubs are sort of abstracting away the details of formatting those messages, waiting for responses, all of those sort of things. All right, so for now, let's think about the good things. All right, let's think about, what joy have I brought to your life with this? All right, well, one, for right now, for this part of O33, we're going to assume that these messages they're sort of well formatted and relatively strictly formatted. So they're going to prevent components from, say, overwriting the memory of other components. That browser isn't going to overwrite the memory of the server. It's on an entirely separate machine. The messages are sort of constrained in what they can do. Additionally, if one component crashes, that's not going to cause the other component to crash typically, right? If I had a second laptop sitting over here and it, exploded, it's concerning, but this laptop would be fine, right? We can also do lots of different things to deal with problems, right? If a client, if my browser, crashes, I can restart it, I can retry things, right? All of this. So these are good things. These are exciting things. This is a model that is used in all sorts of places, all right? It's used to share data on the internet. It's used for remote access. It's used in DNS, which is a system you're going to see next week. It's used all over the place, right? But I have introduced at least one new problem to you. All right, I talked about, being a programmer, wanting to be able to make the same procedure calls that you normally would. And we've seen that we have this, this common way to abstract out the details of sending those messages. All right, the word that we use for this is to say that what we're doing here is a remote procedure call. All right, I'm calling a function, but it's really going to some remote server. All right, remote procedure calls are not the same as just doing a procedure call on a computer. So let's understand more about that. Okay, so we're going to take this same picture, we're going to move it. This is my most exciting animation of the day. All right, no, that wasn't it, but we're going to kind of separate them out, client server, different machines. And I'm spreading them apart like this because I'm really going to care about what is happening in between them, right? I have this client on one machine, I have a server on another machine, and I have a network in between them. That network could be the internet. It could be, maybe it's just MIT's network. Maybe it's a network in a data center somewhere. It could look like many things, but it is a network. And as you will soon find out, networks can be unreliable, right? So let's think about what we're going to do. Okay, so this Katrina's Amazing Web Suite, again, taking over Amazon. All right, so we're going to potentially buy some things. So tell me in the chat, what do you all want to buy on Katrina's Amazing Web Suite this semester? Make it interesting, but not weird. Happiness. Okay, oh my gosh. All right, hang on. Let me take some time to decide which things we're gonna buy. Llamas, hamster, human, oh, guys, we're not gonna buy happiness or human interaction. I can do that for you. It's about my bookshelf, not for sale. Like, oh my goodness, this is great. Okay, we're gonna buy llamas because I think that's gonna have some exciting image options for me during the semester. But these are all nice. Also, not selling you an ECS degree. Okay, so we're gonna buy llamas. I don't know, maybe they're real llamas. Maybe we branch into agriculture. I don't know what our plan is for the semester. So we're browsing llamas. Okay, awesome. So I, view this web page. I request a specific item, a specific llama. That goes to the server. The server gets that request, handles it, does whatever it needs to do. It finds the page with, the best llama and says, okay, I'm gonna send it back. And then it gets lost by the network. Okay, this happens all the time, all right? Probably data that my laptop has been sending to your laptops via Zoom has been lost at some point in this communication. Well, in this case, we can think of things like at an application level and say, oh, okay, I don't know, I'll like refresh the page, right? I'll send this request again. And, yeah, okay, so maybe the next time it gets through, all right? And, this is good. We did a little bit of extra work, right? It's, some part of the system had to be smart enough to say, okay, I'm going to reissue this request, right? And that in itself, that's not incredibly straightforward, right? How do you decide that things have taken sort of long enough? But Okay, we made the request again. We got our llama to view. Very exciting. So now we've picked the best llama, so we're gonna buy it. All right, so similar deal. I sent a request. This time I'm buying my llama, and I'm sending like my credit card number. Okay, so that's what this is. That's what this is about. Same thing happens. The server gets the request, it handles it, right? But that message, it gets lost on the network. Okay, so you sitting there trying to buy your llama, like you're not getting a confirmation page, you know, things aren't happening. Because you say, well, I really want this llama, like I'm very upset. So what if we try the same approach, right? And we get a request back, okay? Yeah, right. For this example, Julian, we're just going to encode the credit card number in the URL in plain text. In May, we'll talk about why that's not a good idea. Today, in February, it's fine. Yeah, so what happened? Oh, stonks. I'm not talking about the stonks in this class, right? Yeah, we have 2 llamas now, which like, okay, sounds amazing, but maybe we only budgeted for 1 llama, okay? This is not what we wanted, okay? This isn't what we wanted to happen. There are ways to handle this, okay? This particular problem, there are ways to deal with this issue, all right? We'll talk about exactly how we might do this. One way though is to give each request sort of its own unique ID, to have the server keep track of that state, right? For it to say like, okay, I already processed this ID. I'm just gonna resend my reply, but not actually purchase the second llama. Okay, there are ways to handle it, right? It's a little complicated. It's a little bit annoying, but there are ways to handle it. But then new problems arise, all right? Suppose I buy a llama, it gets to the server gets my request, and halfway through handling that request, it crashes. Like the server crashes. So what happened, right? Did I buy the llama? Like, did I not? It's like Schrodinger's llama at that point, right? Like, what is up? Okay, this is a lot, all right? It would seem that in our quest to enforce modularity, I've introduced quite a few problems into your life. And indeed I have, all right? And this class is about dealing with those problems, all right? But good news for you all, we will be able to solve all of those, even the server crashing in the middle of the request, all right? We'll be able to solve all of those. And what you will find is that if we start from this modular design, we can reason about all of this, right? Right? We can reason about the components and the interactions between them. We can test modules individually, right? We will find that it's much easier to change the module than the modularity. Also, this has got to be the best question I've ever gotten in lecture. To clarify, does the system crash before or after the llamas are bought? That's the problem, we don't know. From your viewpoint as the client, you don't have a lot of insight to that process, right? In fact, the server sort of might not even know, right? Maybe it submitted your credit card info to whatever verification server has to happen, and it's really, really complicated, right? So we are gonna have to deal with all of those steps. Right? We are going to have to be very precise about the point in this system at which the llama is purchased. It will be so important that it gets a name, all right? And so we are going to solve this. Like, get hyped for April when we can buy a llama successfully, all right? But you know, as long as we're dreaming big, as long as we're thinking about all of the things that we might do with Katrina's amazing web suite, like, let's keep going. Okay, because just dealing with this problem, this is not the only thing we're going to care about. All right, we're going to kind of simplify things a little bit. I'm really just thinking about my client and my server. And you know, again, we're trying to take over Amazon. We're not going to get there if we just have like one client and one server. That's just one person buying a llama at a time. Right? What if we have more than this? Okay, what if we want a lot of clients and a lot of servers? Amazon, that's very good. Okay, these are issues of scalability, right? How does our system behave as it grows, right? And it can grow in a lot of different ways, right? Maybe there are more machines, as I've illustrated here, which might mean more users. It might mean more requests. It might mean more data. All right, it could be a lot of things. And you can think of this isn't just a problem of like how do we make sure that we have enough money to buy enough hardware to handle all of this? It's, you know, looking at this picture. Okay, I have 6 different servers here on there's 6 blue boxes on the right side. You know, are clients allowed to go to any of those servers? Right? Do they have to start at a particular one? Have I partitioned, you know, how clients go to which servers? How do I make sure clients know about those partitions if I've done that? If I say, well, it's okay for a client to communicate with every server, any server, how do I keep that information consistent? Right? How do those servers share information? Remember that there is still a network between all of these machines, right? Things are not going to happen instantaneously. Right now, as you know, we're growing. We've got a lot of machines here. Surely bad things are going to start to happen to us, right? Things are going to start to fail. That could be machines, clients, servers. It could be the network. So how are we going to deal with this? Right? How does our system deal with failures? If a link in the network goes down and messages are lost, what do we do there? Right? As I gave you the example before, what if the server crashes? What if the client crashes? Right? We're thinking of systems that are big enough that this is going to happen. Right? This is going to happen to our system. These types of failures, though, we tend to imagine as being just random failures. All right. So what about, as long as there can be random failures, why not targeted failures, right? What about attacks? Okay. What if people show up? We're going to store some very important, very private information on this system, right? What happens in the face of targeted attacks, right? How should we be storing things here? For instance, in this system, you know, users might have accounts. So they have a username and a password. That means that at some point our system has to do the action of saying, okay, this, you know, user, say Howie, is trying to log in. Howie's inputted a password, and I'm going to check against, you know, the password that I know is correct for him. If I'm just storing Howie's password in plain text somewhere in the system, right, and one of these little purple guys here gets into the system, it could just read all the passwords. That's very bad. All right. So how do we deal with this? Right? How do we keep information secure? What do we do if somebody is trying to bring down parts of our system? What do we do if they're trying to bring down the network in between our system? All right. How do we stand up in the face of those attacks? All right. And then, you know, within all of this, we usually want things to do more than just kind of get by, right? We want things to perform well. So what's going to happen, you know, if things start slowing down? All right, so I went with Turtle for performance issues. I thought that worked okay. All right, so say network links get slower, or some of the machines start to get slow. You know, well, what do we do? How do we define our performance requirements? How do we talk about how well the system should perform? How do we know if our system is even meeting those requirements, right? Like if I tell you that your network connection is running at 10 megabytes per second, do you know if that's good or bad? Right? How do you know? And if it turns out to be bad, what do you do about it? How do you figure out where the problem is, right? If you imagine the system, if we have a server that we think is performing kind of not up to par, right? It's not handling very many requests. We'd have a lot of questions to ask, right? Okay, like are requests just not getting directed to it? Is the network in front of the server slow so that the requests just can't get there fast enough? Are requests getting through, but something about the server itself, like the CPU on the server is slow? Is it running out of storage? Could be any number of things. All right, so how we deal with that can be very complicated. You'll see performance. I've broken these things up, but you'll see performance come up in all of these different areas. So we'll think about performance when we're thinking about scale and fault tolerance and security, right? And then one of the final things that we're going to start to see throughout this class, our design and implementation choices matter, right? They affect people and communities. And so the question of who makes these choices matters. All right, so you're going to see all of this throughout this class. Modularity and abstraction, the principles that I introduced to you earlier, will help you be able to achieve these properties, right? But in virtually every case, we're not going to achieve every good thing here, right? For instance, we might decide that security is more important for a particular system, say like for the back end of a banking website, and trade off something for that, maybe some other type of performance, or maybe even a little bit of simplicity. We might decide, on the other hand, that for some systems, reliability is really important. Maybe for the network that is handling 911 calls, right? Reliability is of the utmost important there. We might trade off something for that, right? We might trade off performance. So this class is all about learning to recognize those trade-offs and learning how to articulate them as you're designing systems and to sort of defend your choices in your design. Right. So this is an exceptionally broad class. One of the cool things about O33, in many schools, if you took a computer systems class, you might focus on one semi-narrow area, right? You might take a class in operating systems or networks or databases. In O33, we're gonna do more than that. So I'll skip to the website so you all can see. I know that you cannot see the entire website on the screen. I'm gonna make it smaller, right? So this is your favorite website now, I assume. All right, so you can see the calendar here, smushed for visual reasons, but normal when you look at it on your own. All right, so you can see we're gonna take you through orange. I'm pointing to it as if you can see my hand. Orange, operating systems, all right? We're gonna talk about that. The problem that an operating system is gonna solve for us is enforcing modularity on a single machine, right? A downside of a client server model is that you need two machines. And maybe you don't want two machines all the time, right? Maybe you just want the one, right? So we'll learn a little bit about how operating systems work. Then we'll start to move on to networking. That's what's in yellow here on the calendar, right? And so we'll ask questions about, well, how does the network sort of in the middle of these systems work, right? How does, for instance, how does data know how to get from one machine to another, right? How do we deal with problems of scale? Right? How are you all managing to get sort of my video feed right now? How does it know where to go? How is it handling so many of you at once? All of that, all right? And what can go wrong? Okay, understanding the network lets us understand how machines communicate, which lets us understand what sort of failures or performance issues might arise, right? And dealing with those failures and other types of failures is gonna come up in the third part of O33, so the green part on this calendar. Right, and here's where we're going to think about distributed systems. So we're thinking big systems at this point that have kind of machines connected via a network. We're going to think about, well, what happens with random failures, right? Clients crash, servers crash, all sorts of machines crash. And then the end of the semester, we're going to start talking about security. You can see a lot of the recitations for security are TBD. It's partly because sometimes we like to see what security problems happen in the world during O33, and then we'll talk about them. So surely something is going to go wrong in the world at some point, right? So this is a lot, this is a lot of technical content. It is a lot of different topics, all right? But you're going to see themes throughout. You're going to see how good design helps us achieve these properties. You're going to see all of the places where we make trade-offs. We're going to consider performance issues at every step. We're going to think about who is affected by our design decisions, who is making those design decisions all throughout. All right. So the way that this is done in O33, well, I'll go back to the top just for fun. So you can see the cool box that shows you what day it is. All right. So in lecture, which is happening to you right now, so you've made it to lecture, this is where I'm going to talk to you sort of about big ideas in the class. Right. This is where you will get most of the narrative that propels you through O33, but it's also where you'll get a lot of the technical content. So for instance, you can see on the site here, this time next week, we are going to be talking about the details of virtual memory, right? And why we use that and how it does and all sorts of things like that, right? In recitations, which happen on Tuesdays and Thursdays, the majority of you went to one yesterday, you will read papers describing successful systems, right? So you're going to get to see a lot of the stuff that I talk about in lecture in action in real systems, right? You will start to get practice analyzing those systems. You'll start to get practice critiquing those systems. You might read some papers in this class where you think, I don't like this. I don't like this design. I would have done this differently. Okay, that's amazing. That's totally fine. All right, for recitation, you should be reading the papers beforehand. All right, so starting tomorrow, you'll come and read the papers, and we'll have all sorts of fun in recitations. Recitations are a very cool time. If you have not already, I can see that TAs are crushing it with recitation section assignments. If you have not logged onto Piazza and filled out that form, please do that today. You can do it right now. All right. On Fridays, this is where you will be in your writing tutorials. And in fact, we have a bunch of the tutorial stuff in lecture today, which is exciting. They're a different color, not because they are not tied into the class, but we really want to call that out as the place where you're going to get the majority of communication, the communication in instruction. All right. And a lot of that instruction is going to be focused around the design project for this class. All right, so the design project, it's a big semester-long project done in teams. The specification will be out this Friday, as you can see. All right, you're going to talk a lot about just how to design systems, how do we choose problems, how do we define trade-offs, how do we structure things. You'll learn how to communicate those ideas. All right, so this design project has a bunch of deliverables, but we will walk you through all of them. You will learn all about them in tutorial. We have some other assignments as well. We have smaller, pretty lightweight hands-on assignments. You can see hands-on DNS here. So you'll just get to interact with some existing systems, all right? Learn things about DNS, learn things about Unix, pretty chill time. And lets you really see that you can interact with these systems as real people in the world, all right? We also have exams. So we have a midterm and we have a final. It's just exam 1 and exam 2. The final is not a cumulative exam. But this is, I'm obviously biased, but this is a pretty fun class, I think. So in addition to the website, all right, also sign up on Piazza. Okay, the final is during finals week. I don't know what day it is yet, but we should know by the 3rd week of class, I think. Piazza is where announcements happen. Okay, so there will be things posted on Piazza that aren't on the website. All of the Zoom links, all right, the Zoom link for lecture and for recitations and tutorials, those are all on Piazza, all right. For Piazza, we're pretty on top of it. Okay, we address administrative questions relatively quickly. We do love when students jump in to answer other students, especially questions about the course content. It's just like a really nice community to have. Plus, there are like a lot of you and less of us for sure. And again, and please give us your information for availability other than the recitations. Talking out, so if you're concerned about participating in recitations or in tutorial, which is where we do a lot of participation, if you're worried about your living situation right now, like maybe you're worried about internet access or access to quiet space, things like that, once you're in your section, let your instructors know. We will work with you to figure out a solution, because we know that this is still like a struggle, right? We're all sort of struggling with this situation we find ourselves in. We will figure out a way to make this class work for you. All right. So what did you see today? It's the first lecture, so we end a little bit early. Don't get used to that. All right. What did you see today? The big theme for 033 is that complexity limits what you can do, right? It limits what you can build. So when we think about designing systems, we think about how to mitigate that, right? We're going to mitigate it with design principles like modularity and abstraction. Also, a student told me once that I say modularity in every lecture. Seems correct. It's really important. All right, so you will see these principles and you'll start to see other design principles. All right, on Monday, we'll talk a little bit about hierarchy, for instance. We'll talk about layering, all sorts of these things. But getting into the details of this, we are going to want modularity in a strong sense, right? We want it to be enforced, right, by some external mechanism. So our systems are so big and so complex. Even though we try to avoid complexity, if something can go wrong, it will, all right? So you've seen now one way to enforce modularity, right? This client server model, right? Which has this idea of the client and server having remote procedure calls between them, right? And that's just to illustrate this idea that, you might call a function on the client that has to send a request to the server, right? It has to make it across a network. That is going to bring us some problems. All right. So in recitation tomorrow, you'll talk about an example of a very complex system that, you know, had some issues. All right. So where are we going in lecture though? On Monday, we're going to talk about naming. All right. Naming is a kind of an abstract concept. It's a principle that allows modules to communicate. Okay. So if you think about it, if that client is sending data to that server, it's going to be able to call the server something, right? It needs a name. You needed a link to get to this Zoom, right? That is an example of a name. Right. Once we get through naming, we're going to start operating systems in earnest, right? Which again enforces modularity on a single machine, right? So we're going to talk quite a bit about that. But like I said, so this is all for. Did you just type the IP address directly into the terminal, Griffin? I would be surprised if you did that. So this is it for today. I'll hang out for questions afterwards. Again, we're ending like 7-8 minutes early, which is normal for the first lecture, but not normal for most O33 lectures. They are timed pretty well. This was very exciting. It's been a very long time since I've seen 260 students on OneSID Zoom. So your recitation instructors will see you tomorrow. You will have tutorial assignments in time for Friday's tutorial, and I will see you all again on Monday, unless people are here for questions.